Good morning, good evening, everyone. So, in the last video, we had talked about monoid semigroups, groupoids, abelian groups, commutative groups. From we take the discussion on from there. So now we talk about finite groups, right? Finite groups and infinite groups. So what is a finite group? If say G is a set and asterisk is an operation and this is a group, then this is a finite if G has a finite number of elements, has finite number of elements, else it is an infinite group, right? Okay, what is the order of a group? Order of a group. In case of a finite group, the number of elements is the order of the group. Number of elements of a finite group, right? So we have this algebraic structure, the set of integers and the operation plus. So I is dot 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 minus 3 minus 2 minus 1 0 1 2, right? The claim is that this is an abelian group. This is an abelian group. How do you prove this is an abelian group? So the first thing you need to prove is closure. Take any two elements, say minus 3 and 2, and you have the operation plus. This is equals to minus 1, belongs to I. So any two elements belongs to I that the closure holds. Next, you have an identity element. And what is that identity element? So say box is the identity element. Say 3 plus box is equal to 3, or box is equal to 0. So 0 is the identity element. Next we have, say A plus B is equal to 0. So A equal to minus B, or B minus B is the inverse of B for all B belongs to I. So every element in I has an inverse. Okay. Next, what is the next property? Associativity. So A plus B plus C is equal to A plus B plus C, as plus is associative for integers, right? Now A plus B is equal to B plus A, as plus is commutative for integers. Hence, the algebraic system plus I plus is an abelian group. Is an abelian group. Okay, there are some properties of groups. One of the property is the left cancellation law. What is the left cancellation law? So what is the left cancellation law? Say A operation B equal to C. Sorry, this is the say A, say B operation A is equal to C operation A. Then according to the left cancellation law, this is the right cancellation law. Just name it the right cancellation law. Then we have B is equal to C. This is the right cancellation law. So basically it's similar to just cancelling out the factor on the right on both sides of the equal to sign. In much a similar way, we have the left cancellation law. So what is the left cancellation law? It's very similar. So A operation B is equal to A operation C. This will imply B is equal to C. Okay. So if F is a group and there's this binary operation plus, this would imply that left and right cancellation laws would hold. Okay, so we have a problem out here. The problem is it claims that G dot is a group, right? And A and B are elements of G. Then the linear equation A dot x equal to B and y dot A equal to B have unique solutions, right? So it has unique solutions, which means x and y, this pair x and y, the solution pair, only one such pair would exist, not more than one pair would exist. How do you prove that? So A belongs to G implies A has an inverse which also belongs to G. So, and also B belongs to G means, oops, sorry, B has an inverse which also belongs to G. Now we take this equation, we multiply both sides by the inverse, we get x is equal to A inverse B. So this is certainly a solution. Because if we substitute A inverse B in this equation x, we have this, and by the associative property, we have A inverse B within brackets dot B, and this is the identity element of G and dot B, which is equal to B. So this is definitely a solution. So A inverse B is a solution. Now we have to prove the solution is unique. How? Suppose x equal to x1 and x equal to x2 are two solutions, right? So A x1 equal to A x2, this implies x1 equal to x2 by left cancellation law, right? Hence the solution is unique. Similarly, we can prove that y A equal to B has a unique solution in G.